to talk about interferometry. So we're going to talk about what it means to have a good interferometer and some different types of interferometers that you probably encounter in a lab setting. And then also we're going to talk about how to align it well and some different techniques to do that. So what are some criteria for a good interferometer? So to get perfect interference between, say, two laser beams, they need to be completely identical. That means, for instance, their polarization needs to be the same, their bandwidth has to be the same, they need to be in the same spatial mode. And one way to quantify that is the visibility. So the visibility is a quantity that can tell you if you have perfect interference or no interference. And you can measure it by taking the output port of an interferometer and shifting the relative phase in the interferometer until you have a maximum and then a minimum. And when you measure this, you measure the visibility. So another relevant quantity is the coherence length. So the coherence length limits the visibility for two beams that are interfering that, say, come from the same laser but go different path lengths. So this quantity is one way to calculate it for a frequency distribution that approximates a Gaussian. And as you can see here, it's inversely proportional to the spread of the bandwidth. And from this graph, you can see that as you have more colors, they start to spread out more so that peaks and troughs are no longer aligned. And so this can help give a pictorial idea of why the two path lengths need to be the same, so that when there's a spread, the electric fields are in sync. And one thing to note is when you're outside the coherence length for, say, a Gaussian spectral distribution, you're not at visibility of 0, but you're actually at a visibility of 0.5. So now let's talk about a few different common types of interferometers. So first, this is a Sagnac Interferometer. The two beams that get interfered are the clockwise path and the counterclockwise path. This one is nice because it's quite stable as far as relative path lengths go. It can be hard to make them. Their environmental vibration is little because the two beams traverse the same path. This finds common uses in the laser gyroscope, and also we use them in entangled photon source. There are many uses for this interferometer and for the other ones we're going to talk about. Next would be the Michelson Interferometer. So this interferometer splits the beam into two paths, bounce off a mirror and come back together. So one thing to note is that each beam traverses its path twice instead of just once. The two paths are completely separate, and also it's really easy to change the relative path length without distorting the alignment by just adjusting the path length of this mirror. So some of the uses you find for this are a version of this is used in LIGO, and then additionally you may use this for testing the coherence length because it's very easy to change the relative path length separation by making one of them much longer than the other. Next is the Mach-Zehnder Interferometer. So this one is yet a little different because each path is its own, but also it's only traversed once. And I would say this is the most difficult to align, and it's also can be difficult to adjust the phase between the two arms without misaligning the interferometer. You find uses with this one commonly in the gas or plasma area, where you can take one of the beams and make it a reference arm, and then the other one you may put a gas or plasma or even like a combustion sample. And then as you monitor or distort or change the sample, you can look at the relative path length or phase shift between the two arms and gain information about what's going on in your sample. Additionally, you will find Mach-Zehnder interferometers in waveguide optics, and they can be used as variable beam splitters and phase shifters. And one way in a waveguide where it's solid state, the way they change the phase shift is they will put a little heater in one arm to locally change the index of refraction to adjust the relative phase between the two path lengths. And one more use that we use it for is you can use this to create time-bend qubits, where one path length is much greater than the other one, and if you send in a laser pulse, out will come two laser pulses displaced in time. And one more final interferometer that we'll talk about today is the Fabry-Perot interferometer. This one is created, but with a cavity with two reflected mirrors, where what's being interfered is not two paths, but maybe the straight through path, and one that's reflected once, and maybe the one that's reflected twice, or 3 times, or 10 times, or 100. So any combination of number of reflection is what could be interfered at the screen. So as far as terminology goes, an interferometer is often when these two can be separated to different distances, whereas with an Etalon, they are often fixed. Some common uses are filtering and spectroscopy, because when you set up this cavity, only certain wavelengths will have the right phase shift to be transmitted, and others will be reflected, so you can use this as a filter. All right, so now we're going to talk about how to align your interferometer. So my first piece of advice is to listen to the laser beam, because it can tell you where you're going wrong. So first off, goal for an interferometer with a laser beam is when it's constructively interfered, you have a nice Gaussian laser beam. When it's destructively interfering, there's no light at all. There's a couple of signs that can tell you where your alignment is off. First off, if you see rings in your laser beam, that means that the two beams have a different amount of defocus. So they're one's diverging or converging more than the other. And then also, if the contrast between the fringes is not very high, that means that your visibility is low. And that, as we discussed earlier, could be due to many things. Most often, it's either due to your polarization of the two paths not being the same, or the path lengths are not the same. Finally, if you see these spaced fringes like this, that means that there is a relative tilt between the two beams, and the direction of the spacing tells you what direction there's a tilt. So if I were to see a beam like this, I would pick vertical or horizontal, and I would say I picked horizontal. I would tilt one of the beams horizontally until there was no more horizontal tilt, and then you would see just vertical tilt. At that point, what you want to do is tilt one of the beams vertically until each of these fringes gets bigger and bigger and bigger until they encompass the whole beam. And then there's no tilt between the beam and your interferometer is aligned. Alright, so that's useful. What we just showed is useful if you can see the beam. Say it's a red laser beam. But there are situations where you can't see the beam. Say it's an IR wave beam, or you're looking at a stream of single photons. Then you run out of luck if you want to use those other techniques. So there's two more that you may find useful. One of them is to just use a single mode fiber. So you can roughly roughly align your beam, say with the IR detector card or with an alignment laser. And then the goal would be to couple both arms into the same single mode fiber. And if you can do that with a high coupling efficiency, then that means that outside of the fiber, that the beams have a high spatial overlap. Better than that, I think, is if you can use a wavefront sensor. If you can use a wavefront sensor to look at the two beams, and one way to do that, or one useful way to do that, is to make one beam your reference beam, where you adjust the wavefront sensor's tip and tilt to 0, and you mark where it is on the screen. And then you adjust the other beam so that it has the centroid in the same position as the first one, and the tip and tilt is 0. At that point, the two beams are in the same spatial mode. So, in conclusion, talked about some things that are necessary for perfect interference, and a few different types of interferometers that people construct in some of their uses. And then lastly, I want you to remember to listen to your laser beam or use a wavefront sensor if you can't see your laser beam. Thank you.